compilers by making a compiler because they're actually quite simple. At least the basic versions of them are simple. Good question. Is the microphone work?
Microphone's for recording only.
Okay, I'll speak up. Cool. So before I start coding a compiler, I just want to talk very high level what a compiler does. So all a compiler is some software that takes code written in one language and changes it into code written in another language. So that might be PHP to C, C to machine code, could be anything to anything. So the reason we need a compiler is because code written for humans to read is really hard for computers to understand, and code written for computers to understand is really hard for humans to understand. So like here's some machine code, like I don't know what that does, I just mashed ones and zeros for a bit. But you know, no one wants to code in that mess. So we code in higher level languages, and then compilers turn those high level languages into lower level languages. So a compiler is made of 3 bits, which is kind of cool, and I'll explain why in a minute. But the first bit is the front end, and it takes the source file, so the file in the language that you're writing in, and it turns it into what we call an intermediate representation. All it means is it just turns it into a version of code that you wouldn't really understand, like you wouldn't expect. It's like a tree structure that you will see later on. The middle end of the compiler makes performance optimizations. So that could be like if you've written some dead code, so that's maybe like an if statement that will never hit its else or something like that. A compiler might just rip that code out because the code doesn't actually need it. And then the back end of the compiler will turn this intermediate representation into the target code. So the reason this is really cool is because whenever you're like dealing with, say you're writing a compiler that wants to compile Ruby down to something, once you've got all the different parts, if you wanted to say compile PHP down to something, the middle and back ends can stay pretty much the same, just change the front end. So you can kind of get this nice sort of thing, or if someone writes a really good way of doing some type of performance optimization, you could add that to your middle end, and your front and back ends don't need to change. That's quite nice. So today, we're going to look at 3 main parts of the compiler. So in the front end, we're going to look at a tokenizer, which is sometimes called a lexer. And we're going to look at a parser. And then in the back end, we're going to look at the code generator. I'm going to hand wave over all the optimization stuff because that shit is super complicated, and that's like a talk by itself. So the tokenizer, so what it does is it takes your code and turns it into understandable chunks. So in this case, we have def hello with some parentheses, and after it's been tokenized, all the tokens get pulled out. So there'll be one for def, there'll be a token that's called an identifier, which will be hello, and then there's a token for the open parentheses and one for the close. That's all it does. The parser will take that all those tokens and turn it into that thing I said earlier, the intermediate representation. So all that means is you've got your list of tokens here. So if we had 1 + 1, that's a token 1, token plus, token 1. And that'll become this little tree structure that says, okay, there's a plus operator and it needs something on its left. There's 1, something on its right, which is 1. And that's like a very simple example of what the intermediate representation might be like. Code generator then, after it's, let's assume that some optimizations have been done, again, hand waving, it will take that intermediate representation and turn it into code. So for example, we might have the same thing we had, so a plus with 1 and 1, and the code it spits out could be a function called add with 1 and 1 instead of 1 + 1. So in our target language, in this example, that is how you would do addition, not with the plus symbol. So that's sort of a very high level overview of some of the stuff that I'll be coding in a second. But before I jump in and do that, I want to do a quick detour and talk about transpilers, because technically what I'm writing soon is a transpiler, and I don't want anyone afterwards going, Toby, you were a transpiler, not a compiler. So basically a transpiler is a compiler. It's just that traditionally compilers go down the way. So like PHP to C, C to machine code, stuff like that. Transpilers stay at the same level of abstraction. So that could be like what I'm going to be doing is Ruby to JavaScript. So they're both high-level languages, so it's sort of going across the way. So like if anyone's used Babel, it's like a JavaScript thing for doing like ES6 stuff. So it's taking fancy JavaScript and changing it into older, less fancy JavaScript. So demo time. Is the size okay? Can people read the stuff on the right-hand side? Sweet. So what we have is a file on the right. This is going to be our source file. So this is a Ruby-like language. So we've got we're defining a method called hello. It takes x and y, and it will call in turn a method called greet, which takes x, and it will take name of y and put it out. And to run this, what we're going to do is type Ruby compile, and so far it does nothing because we haven't done anything yet. So I should say, I'm not going to live code absolutely everything here because it's really boring to watch someone type a lot of words on screen. So I have some shortcuts to like throw in bits of code, and I'll talk through them instead of like angrily missing letters and making typos. So hopefully that works. Yay, look at that. That worked. Done. No. So what we're going to do is we're going to have three classes. We're going to have the tokenizer, we're going to have the parser, and we're going to have the generator. So just to recap, the tokenizer will turn strings into tokens. The parser takes those tokens, makes a wee tree thing, the intermediate representation. And then the generator takes that tree and spits out some JavaScript. So how we're going to do that then is, let's write some sample code. So we're probably going to take our tokenizer. It's going to read the source file, which is this file on the right, and it will call tokenize on it. So now if we run our code, I would hope that it would shout. And it didn't. I didn't save the file. Save the file. Now it's shouting. Sweet. Okay, so first thing, our initializer is wrong. Actually, has anyone done Ruby here? Sweet. Okay, so I might gloss over some stuff in Ruby, just to not like bore you to death, but if anyone has any questions at any time, just shout. So the first thing, we don't have an initializer. So initializer. Oh my goodness, I can't spell. Initializer. So what we want to do is we've got some code that we're passing in. So this is this read, and all we're going to do for now is store that off. A for autocomplete. Oh my goodness. There we go. Okay, so now it's shouting I don't have a tokenize method because we've got this far. So whenever we come to tokenize a thing, if we think about what a tokenizer wants to do, what it wants to do is jump through treat this code on the right-hand side like a string, and sort of for each thing that it thinks is a token, store that information off somewhere. So by the end of it, we should have a list of tokens. So let's get our list sorted first. So here's our we've set it up an array, and we're just going to return an array. Right now, it's completely empty. But what we'll do is we'll shovel in like the output of grabbing one token, and we'll do that until the code is empty. This is like some nice Ruby. So like it'll just keep on looping around. As soon as it says the code is empty, it will stop. Until it is empty, it will continue to keep on grabbing one token. So if I run this, it should shout because we haven't actually made a grab one token method yet. So luckily, I made one earlier. I could not be arsed typing this out because I always get it wrong each time. It's like this stuff here. So what this is doing from line 14, if you can see the numbers yet. So first thing we want to do is strip the string each time, because just like the real language Ruby, our sort of demo Ruby is white space agnostic. So we'll just always trim any white space off the start and end. Then we're going to look through each token type. A token type is a thing I will show shortly. And for each of them, we're going to try and match up. So this is on line 16 here, we've got a little bit of regex going on. So what this is doing is saying, hey, for each iteration through, check to see if the token type we have defined matches a thing. So if it matches, it's going to go into this block. And this block does two things. The first thing it does is it kind of rips that token out of that string. So if we were to go around this and it was defined a token def, first thing it would do is just rip def out because we don't need that anymore. We've tokenized it. And the second thing it'll do is it'll return that new token. If at the end of all this, it gets to the end, it shouldn't, because it means there's a token that we haven't been able to grab. We wanted to throw an error. If I run this, it should shout, because yeah, we haven't actually set our token types yet. So I type this. I definitely wasn't typing this by hand. So these are our token types. So it's an array of arrays, and basically what we have here is in order of importance, the different tokens that our language wants to read. So for every compiler, you would need to sort of list the things that the language is being used, like things that are being used in the language. So we've got def, and an identifier, which is like a variable name or a method name. So like hello, x, stuff like that. An integer, 0 to 9. An open paren, a closed paren, and a comma. So these are all the things that our language supports. And then on the right of all these, if you haven't seen regular expressions before, don't worry. But basically all these do is, like this def says that in order for it to be considered a def, there needs to be exactly the letters DEF, I could select stuff, DEF, surrounded by a word boundary, which just basically means it's either at the start of the string or there's white space around it. And we do that for all these things. So like for an integer, we're saying we can have, the plus means as many as we want, things that are 0 to 9 altogether, so long as there's this word boundary around them. We don't need word boundaries for like these parens or commas, because in our language, there should never be like a word boundary between like that paren and the thing before it. So now we have this, we should hopefully get one more error, which is, yeah, so we've got as far now, so our code should be running and trying to return a token, but we haven't defined what a token is yet. So I'm going to do that here. I don't know if anyone has used structs before in Ruby, but they're a really handy way of encapsulating data. So normally we would talk about throwing around hashes or arrays or strings or whatever. And that's cool until you hit a problem and your code just says, ooh, undefined thing for null. And it's like, shit, I have no idea what that means. If you put it into a struct, then it gives it some semantic meaning, because now we're throwing about tokens, not strings. So it'll say, hey, undefined thing for token. So it kind of points you in the right direction. And you just do that by doing, you give it a name, you do struct.new, and then you pass in the attributes that you'll eventually want. So for us, what we care about is the type, which is the type of the token, and the value. So for example, hello should be a type of identifier, because we've said an identifier is any lowercase or uppercase series of characters, and its name in this case would be hello. So if we run this, we have finished the first part of our compiler. So what we have here is a big old list of the the tokens that are in our source file. So with this information, we can say that according to our compiler, this language has at least been written vaguely right. So you haven't like made any egregious mistakes in the code. And that is the end of the tokenizer part. So let me get rid of that. Okay. So next up comes the parser. So as I said before, the parser takes these tokens and then turns them into something that the compiler can actually do something with. So the way it works is we're going to create a tree sort of structure. And what we'll do is we'll pass the tokens in and call parse on them. Let me just comment this out. And we know from earlier that the first thing it's going to do is shout that I don't have an initializer. So that's just create one. And we'll just do the exact same thing. So we'll just read in some tokens and store them off in a variable that we can access later. Let's run this. It doesn't like parsing. Sweet. So we'll create a wee parse method. So the way parsing works is you need to sort of tell the compiler, hey, this is the semantics of our language. So for example, in our language, we're saying that in order for like a def to be a thing, it needs to have the keyword def, and then it needs to have some type of identifier, and then potentially some type of parameters going into it, and then it has to do a thing, and it has to end with the word end. If none of those things happen, then this isn't valid code. So how we're going to do that is, what are we going to do for that? We're going to create a def node struct. So this is what's going to get returned at the end. And what we want out of this is kind of as I described there. So we know that for a def, it's going to have a name because it's got an identifier with a name. It's going to have some arguments, and it's going to have to do something inside it. So that's the body sort of part here. So in order to get that information, what we're going to start having to do is consuming these tokens. So there's some tokens in our code and in all code that are needed by the language but don't have any real value. For example, def, like it is needed to tell you that, oh, this is like a function or a method that I'm defining. But once you know that, you don't actually need to know like the def was there, just that it had been there at some point. So the way we would do this is we could write a consume method, and what this would do is look for a particular token, and if it exists, just boot it off the stack because we're happy that it was there. So we could consume something like that, and I will write the consume method shortly, and we'll sort of see that in action. For the argument names, we're going to push that off to the side for now because that'll require a bit more thinking and playing about. The body will do the same thing. So I'm just like hard coding some strings in here just so it doesn't blow up in our face immediately. And then so once we've parsed the body, we'll assume we have to consume the end token. And then that should be us good to go. So let me just run this. Doesn't like that there's no consume. That is fine. So what is my shortcut for doing consume? Way. So when we're consuming stuff, as I say, what we kind of want to do is push it off the array of tokens that we have. So the first thing we'll do is in Ruby, we can do shift. And what shift will do is just take the first element off an array, pop it off, and we can store it in our case, a variable called token. So each time through this, it should shrink that array by 1. And if the token type is the same as the expected token, then that's cool, and we just return the token, end of method. If not, what we'll do is we'll raise a runtime error, and we'll just give ourselves like a helping hand by saying, okay, we expected the token type to be this, but we got this. Does that make sense? Sweet. So, okay, here we go. So expected token type end, but got identifier. So what that means is up here somewhere, it managed to consume def. That's fine. We then did some hand waving, and then we said, okay, you should consume end. But what's happened is because we haven't consumed any other tokens, we've only got this far in our source code, just to the hello bit. So it found an identifier whenever it went to do that. So let's fix that now. So that's our argument names. Oh, I missed a bit actually. First thing we should do is let's just consume that name. So here we're just saying grab the identifier, and that should pull back a token if all was good. And on a token, we can ask for its value. The reason we can do that is in our struct, we said it has a type and a value. So we can call .value on it. So that should get us our name. And then for the argument names, we need to parse these arguments. Now that's not just as simple as writing consume a whole bunch of times, because there's an arbitrary amount of arguments that we can have. So we need to write some code to do that. So luckily I wrote some earlier, and it looks like this. So what we have here is we're setting up an array, and we are always consuming an open paren. So we're saying in our language that you have to have an open paren. You can't just write def name and leave it blank. So we look for an open paren. Then we're going to peek ahead and go, right, is the next thing an identifier? If it is, we'll do some stuff. If it's not, it means we don't have any argument names. It's just an open paren and a closed paren. So we'll look ahead. And then what we'll do is, if there is an identifier, we will consume it here and just pop it into that argument names array. And then because there's a indefinite amount of these things, we'll go into a while loop, and we'll just keep on looking for a comma. And this allows us just to have, this could be as long as we wanted it to be. And I'll just keep on going, consuming commas and the identifier each time. And then at the end, it'll always look for a closed paren, and it'll just return the array. Let's see. Okay, so it didn't like that we didn't have a peek method. That's fair enough. So we'll just quickly write peak method. So what peak will need to do is look for an expected token, and it should also probably look for an index, because in that example there, we only care about peaking one ahead, but we might want to look a couple ahead to see what else might be sort of in our future in the code. And all we'll want to do here is, instead of like before we were shifting stuff off the array, this time we'll just look at the array, the given index, which should be 0 by default. And we just want to see if its type is the same as the expected type, or expected token. So if it is, it'll return true, and stuff like our stuff like our peak will return true, and if it's not, it'll return false. And whenever while sees a false, it'll just stop executing. Let's see how far we get now. Okay, back to our old friend. It's looking for this end prematurely, and it's because we haven't done the parsed body part yet. So to parse the body, what do we need to do for that? Need to do this. I don't know why, but this is my favorite bit of the code, and I'm gonna get. I don't even know why I get excited about it, but this I think is really powerful. So it'll peek ahead and see if it's an integer. If it is, it'll just go, hey, I'll try and parse an integer. If it peeks ahead and sees an identifier and then immediately sees an open paren, it'll go, hey, I need to parse a call, because it's like a function being called or something. And if it doesn't find any of those two, in our language, we're saying, okay, it's probably a variable. Let's just parse a variable. So what we'll do here is, if we change this source code to be a 1, so what I want to do is hit these easier ones first. So what we're saying is that now our code will just always just return 1. So if we do this, it should crop itself, because yeah, it can't parse an integer because we haven't defined that yet. Parsing an integer is quite easy. So whenever we're parsing an integer, what we'll want to do is return an integer node. And it'll just have a value. So that'll be consuming the integer, should have, and grabbing its value. So this is another struct that we need to make. So let's go down and make that. No, oh my goodness. Oh my goodness. There we go. Oh. So that's just a struct, and it only has one thing, which is a value, because it's an integer. Can't really say too much about it. While I'm here, I'm going to make a variable node. I type variable and not integer. And it's going to be the exact same thing. So it's just going to be a really simple thing that has a value. So remember, with a compiler, it doesn't care about like the values of variables the same way you're executing code would. All this cares about is the token that represents that it's a variable. Okay, so now we've got that, we should be able to. What didn't I like about that? Oh, I didn't define a def node as a struct. Let's do that. Def node that. So the reason I keep on calling these nodes is because what we're building here, and we should hopefully see this at the end, is a tree. And in sort of techie terms, like a tree is just a series of nodes that are linked together. So the power of this is that once we have this tree, it's a very flexible structure to do stuff with later. Sweet. Okay, so this is our first tree that we've made then. So it looks like crap, but it is a tree, I promise. So what it is it is a def node to begin with. It has a name hello. It has some argument names, X, Y, and Z. And it has a body, and that body points to another node. And in this case, the other node is an integer node that has a value of 1. If we make this a bit more complicated and throw in a variable, it should crop itself because it can't parse a variable. And this will be super easy because it is just like parsing an integer, except we return a variable node. And instead of this, we will be consuming a identifier. Oh, identifier. Try that. Boom. Okay, right. So this one, again, really simple. It just has, instead of a body of an integer node, it's a variable node. If we go back to our actual example, this is a lot more interesting because it has a mixture of variables, other methods. Those methods have inputs going into them, stuff like that. So this is where I really like this parse body because we're now stuck on this parse call. So let's write that the same way we've been in parse integer and parse variable. So the parse call, we think about it, what it needs to do is it's going to take a identifier, like in this case greet, and then it's going to take the argument expressions for that, so like all this stuff, like after greet. So, and it's going to return, we'll call it a call node, because I called everything else a something node. And it'll take a name and some argument expressions. I'm calling them argument expressions instead of argument names because in our first sort of example, these parameters are just like dumb parameters. They're just variable names and commas. But this is an actual, these are expressions because you can have extra stuff going in them, like other methods and stuff. So unfortunately, we can't just steal this parse arguments code. It's kind of similar, but not exactly the same because there's more funky stuff needs to happen. Oh, I've lost where I am. Here we go. To set the name, that's pretty easy. We've been doing this already. We just need identifier and grab the value and set it. And then for these argument expressions, what we'll do is we'll make a new method called parse argument expressions. Oh my goodness. So the reason I'm trying to, like, it's always good practice. Like, I could have thrown all this stuff in here and it would have maybe made sense. But like, see if you can keep your methods to like, where possible, like as small as possible, like it's just as small as you can. It just helps so much with readability later. And also, I'm dealing with a really small screen, so it's kind of good to be able to see them all in one area. So to parse our argument expressions, we should. Oh, see how long this would have been if I had to write all this out. Right. So kind of the same as the whenever we're parsing our parameters, but so we set up an empty array. We look for an open paren. We look to see if there is a closed paren. If there is, we can just continue on. So we'll go on down. We'd consume it on line 98 here, and we would just put it out. If there is no closed paren, then what we want to do, this is the bit that's class, right? So what we're going to do is we're going to parse the body. And we've already defined parsing the body. That's back to this amazing little guy here. So we're getting what's called recursion happening, because what it's going to do is every time it meets this thing, it's going to parse, it's going to call it like a method that it previously called it. And then it's going to go, oh, is this integer, or is it a call, or is it a variable? If it's a call, it'll go back into this via the parse call and in the parse argument express. Sorry, I'm talking really fast because this excites me. So it's going to keep on sort of going through, and this allows us to get arbitrarily deep with this stuff. Like, we can just keep on passing new method names into this thing, like just as deep as we want to go. And it will just always handle it because it's just going to keep on, like, we don't have to write like confusing nested code. We can just keep on calling code that ends up calling us again until there's some sort of stop condition. In our case, it's just whenever it runs out of things, the sort of go in. So it'll keep on sort of bubbling down, and then it'll sort of start going back up again while it goes through this while loop. So it'll keep on looking for commas, and it'll keep on consuming those commas and then parsing the body again. The cycle keeps on going round and round and round. I'm going to undo all these changes because I don't know if I made a mistake when I was typing that. And I did. What did I do wrong? Oh, so I haven't made the call node because I seem to hate defining structs. Grab this. Does that make sense, by the way, what I said about recursion? I got a bit excited and didn't really say too much. What am I making here? Call node. Sweet. Okay, so here we actually have a properly confusing tree. So we have our def node still called hello. We've only got two argument names now, x and y. And then our body is a call node. It has a name of greet. But then the argument expressions for it are a variable node and then another call node. That call node has a name and argument expressions itself. And this is sort of where it gets really powerful because we'll just keep on going down. It'll keep on getting bigger and bigger and bigger, but without any extra code. So we've got our tree now. So we're 90% of the way there. We just need to turn this tree into some JavaScript, which is great because I'm thirsty and it's getting near the end of the talk. So what we want to do is make a new generator. And as I said in the talk earlier, that will take this intermediate representation, this tree structure, and generate some code. So because it is getting near the end and I'm getting tired, I'm going to be really lazy and do this one more time. And this is the final bit of code. So, oh man, it's so small on the screen. Right. What I'm going to do is comment out this. So what we have here is a single method called generate. And that will take a node. Because remember, we're always just dealing in nodes that link to other nodes. What it's going to do is open up a case statement. Now, in Ruby, cases work in a really interesting and confusing way where you can pass in the name of the class that you want to compare to, and it just magically works. So normally you'd put in the value, but putting in classes just it doesn't seem to mind and is like pragmatic Ruby mentally. But so what we'll do is for each of our nodes, we will do something different. So for variable nodes and integer nodes, they're really dull nodes. They just have a value. We'll just spit them out. For the other two nodes, which are our def node and our call node, we'll actually do something a bit fancy, and I'll explain that shortly. Finally, if there's a node that slips through the cracks, we'll help ourselves out by raising a runtime error and like spitting out the node that we couldn't handle with this. It's always a good idea when you're writing code actually to put in these type of else's because it just super helps you out. Instead of getting like a blank result, you get a hey, something should have happened here. And runtime error you just get for free with Ruby. Just call it runtime error.new and the string. It's pretty good. So if we run this, we immediately get this exception raised, and it's because we're not handling this def node thing. So let's go ahead and uncomment this, and I will talk you through this. So this is our first bit of JavaScript. So this is the target language that we're trying to spit this stuff out to. And in JavaScript, in old boring versions of JavaScript, this is how you would write it. So you need a function instead of def. You would have then some name for your function name. You would have some arguments. And then you got the syntactic need to have curly braces. JavaScript, you have to do an explicit return instead of an implicit return. So we'll put that in. And we'll put out the thing that it's returning. So I'll explain these S's, these percent S's. So basically, this is you've made this template out of this string, and in Ruby you can do that, and then with the percent operator, and then by passing in an array, you can go, hey, fill in these percent S's, or there's like S means string, there's D for digit and stuff, but fill in that stuff with the result of the array that we pass in. So for this first one, we want the name of def node, hello in our case. So we'll just call node.name, and we'll get that. For the argument names, we can see if we look on our output, here's our argument names. It's an array. So what we'll do is we'll just join that array with a comma. So that should put out x, comma, y. And then we're going to do recursion again, because now we want to take the body of that and generate everything all over again. So we call generate again, pass in the body node. It's going to go back into this generate method with the node and handle whatever comes in here. So in our case, call node should be the next node. If I run this, it should shout, yeah, because call node hasn't been defined. Call call node is our last thing we need to do. And basically what we're saying here is in JavaScript, a call is a method name with a paren with some stuff happening in it. And again, we can use this formatter to say, okay, the first one should be the name. It's easy enough, node.name. And then for the expression, so that's all these other, go back here, all these other individual nodes, we'll just loop over them using the map. And for each of them, we'll just generate everything all over again. And we'll just keep on doing that. And then we'll join them with a comma. So if I have done all this right and run, we get some JavaScript out. So so I'm so glad that happened. So yeah, so that's like a really basic idea of what a compiler would do. Obviously, in the real world, they act a lot like this is really shit code. Like in the real world, it would be good code, it would be optimized, it would do extra stuff. The greet method inside, because we're not defining a function here, we're just calling a function. If I did, let's see if this works. I haven't made the compiler handle this, so I'm not sure if this will work. But no, because it doesn't expect another def to be inside a def. But yeah, it's because in our sample language, we're only calling stuff, not defining stuff. Yeah. Yes. Yes. Oh, what am I doing? Yeah. That's why. But we could like add extra stuff to this. And this is what I was saying before about the different like having this front, middle, and back end. Like this, in our case, our generator is our back end. So we could really easily change this to be like, you know, okay, I forgot a semicolon there actually. So really to stop JavaScript shouting, I would do that. I didn't have to change the rest of anything else. And if I wanted to compile this into Python, I would do, I actually have no idea how to write Python, but you know, probably something like this, and there's like white space and all that stuff, right? But yeah, so you'd just be changing the generator, not anything else, which is pretty cool. So, demo's done, talk's done. So what we've covered, a compiler, it's just a program. It's just doing normal programming things. Doesn't do anything particularly fancy. Just, you know, take some strings, changes them about, like we're doing for absolutely everything else in computers. The main parts of the compiler, back, middle, and front ends. We looked at the tokenizer, parser, code generator. So we talked about the difference between a transpiler and a compiler, and how you could make a very quick and dirty compiler. So thank you. I want to thank Destroy All Software because I stole a lot of code off one of the screencasts that they put out. All the slides and the code is up on GitHub if you want it. And if you have any questions, happy to answer them now, or if you want to send a DM on Twitter or anything like that, that's all cool. And as was mentioned earlier, we have a simple CS thing. So this was just an attempt to try and start writing posts that assume no knowledge and explain computer science stuff. It is really in its infancy. So if there's ever a term that anyone's heard and goes, holy shit, I have no idea what that is, I shouldn't be here, just tweet me and I will write an article to show that it's actually really simple, because all this stuff isn't that hard. It's just old men using confusing terms most of the time. So yeah, that's it. Thank you very much. Questions? No?
So good.
Cheers. Yeah, super clear. Yeah. Oh. So Ruby is, sorry, the question, if not everyone heard, was, does Ruby get converted to bytecode? So Ruby is actually built in C. So the compiler for it, or the underlying language is built in C. So whenever you whenever Ruby is getting compiled, it happens through C, and then we'll go down to bytecode, or sorry, machine code. Ruby's changing actually. What they do at the moment is like normal sort of compilation, which is this here. But soon they're moving to what's called just-in-time compilation, where it will basically try and only compile little parts of Ruby as it goes. So it's sort of I'm going to hand wave over some of that because it's quite a complicated thing that needs more slides and sort of pointing at it. But yeah. Sorry, so the question was, why did I choose JavaScript? The main reason was I figure most users are makers, so you do JavaScript and Ruby. So I was like, hey, I'll pick two languages that you might know. But so lots of things already do compile to JavaScript. So JavaScript is never used as like the base low-level thing that the computer read. But because browsers can understand and talk in JavaScript, there's a lot of languages like TypeScript, or there's like CoffeeScript. There's like even there's a functional one that I'm blanking on. Anyway, there's yes, but only in yes, I was thinking of Elm. Thank you. They are supersets, but only so much. Like they're defined as a superset because they compile to JavaScript. Like they contain everything and more that JavaScript is in. So it still goes through a compilation process to get there. And yeah, like I mean, the main reason I did pick it was because it's like an arbitrary like showing that these are two different languages that can talk. Yeah, so I would check out like things like Elm. And stuff like that if you actually do hit JavaScript and want to get away from writing so much of it. But yeah, I don't know why. Like, I mean, there's no, like, I mean, the power of JavaScript in the front end is that, you know, it can talk nicely with your DOM and, you know, all that type of stuff. So it would be a weird context switch to be writing a more back-end like code that still interacted with all that stuff after it was compiled. So I wonder if that's maybe why people haven't pushed that type of thing. I think it would feel a bit weird writing code that would act in that sort of way. Yeah. It's
Great, we have more beer. So just stick around.